Hello everyone. This is our first makeup lecture. So because I'll be out of town this week, attending conference, so I will provide the makeup lectures using videos, recorded videos. Okay. As mentioned in our last Friday's class, instead of continuing talking about synchronization, we will start a new chapter on CPU scheduling. Right? The reason is that I still prefer using the blackboard explaining synchronization. That makes it much easier for me to explain the problems and solutions step by step. Okay, so in this recorded videos, we will be talking about a CPU scheduling, okay, in chapter 6. Right, so you can watch these videos when you have time, but do watch them and read the textbook, read chapter 6, and do the problems that I leave at the end of this chapter, because these materials will be included in the midterm. Okay, so now let's start chapter 6, CPU scheduling, okay, and we will resume our discussion on synchronization and finish up chapter 5 after I come back next week. Okay. So before we talk about CPU scheduler, okay, first let's review the different types of schedulers, okay, we have learned so far. Okay, so we have learned that there are three levels of schedulers on a computer. Okay. We have the long-term scheduler, which is also called job scheduler. What it does is it selects which processes should be brought into the ready queue. And then we have the short-term scheduler. It is also called CPU scheduler. From all the processes that are brought into the ready queue by the long-term scheduler, the short-term scheduler or the CPU scheduler decides which process should be run next. Okay? So it selects from the amount of processes that are ready to execute and allocates CPU to one of them. We have also learned that there may also be a medium-term scheduler. So among all the processes that are in the ready queue, ready to run, it decides which process should be temporarily swapped out of memory onto the secondary storage. Okay, and those are the processes that will be temporarily paused, okay, and swapped out, and they might be brought back into memory and placed back into ready queue later. Okay, so these are the three levels of scheduling we have learned so far. Well, you might have realized that on your laptop and desktop, for example, you don't really have long-term scheduler. Right? So how do you decide which process gets admitted and brought into the ready queue? Basically, when you run a process, when you run a program, and when you type a command line and run your program, for example, or double-click it to run it, that's when your program becomes a process, and that's when your process gets admitted and placed into the ready queue. Right? So we don't really have a long-term scheduler on a personal computer. Right? But imagine now if we're talking about a high-end computer, maybe a supercomputer, right? If we consider the supercomputer as a single computer, and then we do have the need for long-term scheduler, because we cannot just admit any process that's started, okay, by any user. Okay, so we have to decide which programs, which applications can be admitted and can be brought into ready queue. Okay, but on our personal computers, for example, we don't really have a long-term scheduler, but we do have both short-term scheduler and medium-term scheduler. Okay, these two levels. Modern operating system, they all have these two levels of schedulers. Okay. So just help you review these basic concepts and understand what these different schedulers do and whether we have them, okay, on our own computers. All right. So now let's focus on the short-term scheduler, aka CPU scheduler. Okay, that's the main topic of chapter 6. Okay, just remember what it does is it selects from the processes that are in the ready queue and allocates CPU to one of them. So let's start with some basic concepts first. Okay, well, we talked about this before. Right? Any process we have this repeated pattern of a CPU burst and I/O burst. Okay, so the process execution consists of a cycle of a CPU execution and I/O wait. Most of processes, typical process, they all follow this repeated pattern. Okay, so not only that, okay, if we measure the span of the CPU burst of a process, okay, if we do that for all the processes that we have on the computer, and then we can illustrate the distribution of the CPU burst duration using histogram. Right? Everybody understand what is a histogram? It shows the frequency of different values of a particular variable. Okay. Now, in our case, this variable we're looking at is the CPU burst duration. Okay, in milliseconds. Right? That's the x-axis. Okay, and so we have the CPU burst duration ranging from 0 millisecond, okay, to all the way to 40 milliseconds. Okay, and on the y-axis, then we have the frequency. Okay. So notice that most of the processes, right, they have very small, CPU burst durations. Okay, most of them are under 4 milliseconds. Okay, and as the CPU burst duration increases, the frequency of the process drops quickly, really fast. Okay, so this tells us that most of the processes have really short CPU bursts. Okay, and only a very small number of the processes have long CPU bursts. Okay, and their percentage drops really quickly as the CPU burst duration increases. Okay, the distribution generally follows a exponential or hyper-exponential distribution. Okay, so these are the two important observations. Okay, that we will use later on to design and implement CPU schedulers. Well, we will use to understand how the existing CPU scheduling algorithms are designed. Okay, so these are two observations. One is that any process have this repeated CPU burst and I/O wait pattern. Okay, that's CPU and then wait on I/O and then that's CPU again. And the second is that most of the process, the CPU burst duration is really short. Okay, so this slide basically using example to illustrate the CPU burst and I/O burst pattern. Okay, so it's looking at the sequence of execution of one process, right? So this process does first does some computation, right? That's the CPU burst. We use load and store instructions for memory accesses, and then with the data and the operands and the operator and operands, right? Coming from the program and loaded from the memory, then it does the computation using add, for example, right? Add or subtract or multiply or division, right? That's a computation, and that's what basically what the CPU burst is about. Okay, memory accesses and the computations. After it is done, right, then it will go on to do some I/O, right? For example, it needs to read from a file, it needs to read some input from the file, okay, and then the process is in its I/O burst, okay, during which it's essentially waiting for I/O, and after the data that it requires is read, okay, it's read into memory, and then it can consume the data and do more computation, right? So now we have a CPU burst again, and after the computation is done, and then maybe the process needs to write the result back to output file, right? So and then we have another I/O burst. Okay, so this pattern basically repeats. Okay, and in this example, the I/Os we're talking about are file I/Os, right? Reading from the input file and writing to the output file, for example, right? But there can be other types of I/Os. For example, the process needs to read the input from the keyboard, right? And output the result to the display, right? Those are I/Os too. Okay, but no matter what kind of I/O, this CPU burst and I/O burst pattern is generally followed by typical processes. Okay, so these are the observations, right? The CPU burst, I/O burst pattern, and the short duration of a CPU burst. Okay, the CPU schedulers are designed based on. Okay. So now before we look at the scheduling algorithms, okay, first let's look at how the CPU schedule can be implemented. Okay, when can a CPU schedule make a decision? Okay, when can it make a decision? So so first of all, now we know that, right, CPU scheduler is also called system scheduler. It decides which processes that are ready to run should run next. Okay, so in order to understand when a CPU scheduler can make a decision, right? Let's first review the state, right? The state diagram, the life cycle of a process, okay? Because then we will use this different state, okay, to explain when a CPU scheduler can make a decision, okay? So first, let's review this state diagram, okay? So we start from the new, right? That's when a process is created. The process is a new process, okay? Then if we have a long-term scheduler, which is so-called job scheduler, then it will decide when the process should be admitted, okay, into the ready queue. But if we don't have a long-term scheduler, okay, then the new process is immediately admitted into the system and placed into the ready queue, okay. Now, once the process is in the ready queue, the process can run next. Okay, it is waiting for the CPU scheduler to decide when it's time to run. Okay, so when the CPU scheduler decides the process should run next, right? Then the process will change its state to running state. Okay, and that's when the process is actually running at the processor. Well, when the process is running, okay, it may have to leave the processor before it finishes its entire execution. Okay, that can be caused by an interrupt. Okay, when interrupt happens, we have learned that there are different types of interrupts. Right, it can be caused by hardware errors. It can be caused by IOs, for example. Okay, so whenever interrupt happens, the OS has to be invoked to handle the interrupt. Right, while the OS is running, the process that was interrupted, okay, needs to be moved out of processor and placed back into the ready queue. That's one possibility. Okay, it is also possible that the process while it is running, it voluntarily gives up the processor because it has to wait for an I/O. Okay, because it has made a I/O request. Okay, then it has to wait for the I/O to complete. Or maybe the process is waiting for an event. Okay, so now after talking about synchronization, right, after learning chapter 5, we understand what an event can be. Right, for example, it can be a wait, right, on a semaphore. Right, so when the process calls the wait operation on a semaphore, and if the semaphore is not available, meaning that the value of semaphore is less or equal to 0, right, and then this process has to wait for the semaphore to become available. Right, and then when that happens, the process is also moved from the running state to the waiting state. Okay, and we have learned that if the process is waiting for the I/O to complete, the process will be placed on the waiting queue of the particular I/O device. If a process is waiting for a synchronization event to happen, the process will be placed on the synchronization variable. For example, the semaphore's waiting queue. Okay, so. And when the event or when the I/O that the process is waiting on is completed, then the process can be moved back from the waiting queue to the ready queue. Okay, notice that the process is not immediately moved to the running state yet. Okay, because we don't know whether it is this process turn to run next. So we have to first put the process back to the ready queue, and so that it can be scheduled by the CPU scheduler later on. Okay, and finally, when the process finishes entire execution, then it will exit. Okay, and then it's changed to the finished state, to the terminated state. Okay, and we have also learned that this exit happens when the process makes the exit system call. Okay, so now we have reviewed this state diagram. Okay, now we'll come back to the previous slide. Okay, let me explain when decisions can be made. Okay, by a CPU scheduler. So the CPU schedule decision may take place when a process switches from running state to waiting state. That's the first case. Okay. So this happens. Right, this happens here. Let me erase what I just did. Okay. So this happens here. Right. Come back. Okay. This happens here. Right. This is when the process voluntarily gives up the CPU because the process is either waiting for I/O or waiting for an event. Okay, while the process voluntarily gives up the processor, the CPU scheduler now has the ability to decide which process to run next. Okay, so that's the first case. Now, in the second case, the second case, well, the CPU scheduler can make a scheduling decision. That's when the process switches from running state to the ready state. Okay, that corresponds to this arrow here, right? So we know that this happens because there is an interrupt. There was an interrupt, and the process that was running on the processor is interrupted. Is forced to leave the processor so that the OS comes back and handle the interrupt. After the OS finishes handling the interrupt, the CPU scheduler, which is a component of the OS, now also has the opportunity to decide which one to run. Right? So notice that the process that will be run next after the interrupt handling may not be the process that was interrupted before, okay, the interrupt handling. Okay, because the CPU scheduler might make a different decision. Okay, it might choose a different process to run. Okay, although the process that was interrupted, okay, is a different process. Okay, that's the second case. Now, in the third case, okay, the CPU scheduler can make a decision when a process switches from waiting state to ready state, and that corresponds to this arrow here. Okay, so when the I/O completes, or when an event completes, right? This is the I/O event that the process is waiting on. Right? That will signal the OS and also give the CPU scheduler an opportunity to decide which one to run. Okay, so again, right? So the process that will be run next may not be the process that was waiting on the event or waiting on the I/O. Okay, the CPU scheduler might make a different decision. Okay, so that's the third case. Finally, the CPU scheduler can make a decision when the process that was running before terminates. Okay, this is obvious, right? When the process finishes and it vacates the processor, so of course the CPU scheduler now can make a decision which process to run next. Okay. So these are all the four possibilities when a CPU scheduler can make a decision. Okay. Now, with this understanding, okay, then we can talk about an important concept in CPU scheduling that's called preemption. Okay, so what does it mean? Right? So if the CPU scheduling decision is made under case 1 and case 4, okay, then we call it non-preemptive. Okay. So why is that? Right? Because you remember in the first case, right, the CPU scheduler can make a decision because the process that was running before, okay, voluntarily give us CPU. This arrow here, because it has to wait for I/O or event. Okay, so the process that is running before voluntarily give us CPU. Okay, so you can so the non-preemptive, it basically means voluntarily. Okay, in the fourth case, that's when the process finishes execution. Right, also the process voluntarily give us the processor because it has done its entire job. Okay, so on both of these two cases, 1 and 4, right, the CPU scheduler gets involved because the process that was running before voluntarily give up CPU. Okay, so that's why it's called. So under case 1 and case 4, it is called non-preemptive scheduling. Okay, well, under case 2 and case 3, okay, when the CPU scheduler makes a decision, okay, then that is it's called preemptive scheduling. Okay, why? Because under case 2, that is when the process was interrupted. It corresponds to this arrow here. The process was interrupted and it was forced to leave the processor, and that gives the CPU scheduler to make a decision, give the opportunity to make a scheduling decision. Okay, under case 3, that's when the process that was waiting on the event or I/O completes. Okay, now that event or I/O has completed. Okay, so that signal also gives the OS an opportunity to make a CPU scheduling decision. Okay, and that decision would force whichever process that was running on the processor to leave. Okay, and bring a potentially different process back to the processor. Okay, so on the case 2 and case 3, we call it preemptive. Okay, so now you understand preemptive is the opposite of voluntarily. Okay, so under preemptive scheduling, the process that was running on the processor is forced to leave the processor. Okay, under non-preemptive scheduling, the process that is running on the processor voluntarily gives up the processor. Okay, so that's the main difference. Okay, between preemptive scheduling and the non-preemptive. Okay, Okay, now I hope you understand the difference between them. Okay, so just consider, so non-preemptive means the same as voluntarily. Okay. So now, before we talk about specific scheduling algorithm, let's first look at the scheduling criteria. Okay, because scheduling algorithms are generally designed according to some specific criteria. Okay, so first let's look at what are the possible metrics we can consider when we design a scheduling algorithm. Okay, the first metric is CPU utilization. Okay, so CPU utilization, obviously we want to maximize it. Okay, so utilization is a metric, and maximizing CPU utilization would be our criteria or our objective. Okay, so we want to keep the CPU as busy as possible as long as there are processes waiting to be run. Right, that is straightforward. Right, so that can be an important criteria. Okay. The second is throughput. Okay. Throughput means the total number of processes that complete their execution per unit of time. Okay. So throughput is closely related to CPU utilization, but it is looking at the problem from a different perspective. When we talk about CPU utilization, we're looking from the perspective of the hardware. We want to make the hardware as busy as possible, right? So given every 1 second, how many milliseconds the CPU is busy, for example. Okay. But when we look at the throughput, we're looking at it from the perspective of the application, the processes, right? We're looking at every 1 second, for example, how many processes complete their execution. Okay, so they are closely related. Obviously, if we want to maximize the throughput, then we also must maximize the CPU utilization. Okay? But they are looking at the problem from two different perspectives. Okay, and both metrics are looking at the problem from the system perspective. Right? We're looking at the overall performance of the whole system. Okay, CPU utilization is looking at the overall performance of the entire CPU, while throughput is looking at the overall system performance from all the processes in the system. Okay, so the next metric is turnaround time. So turnaround time then is different from throughput because it is looking at the performance of a single process. Okay. Turnaround time is defined as the amount of time to execute a particular process. Okay, so you see the throughput, we are looking at the overall performance. We are looking at the performance of all the processes measured by the number of processes finishing execution within a unit amount of time. While turnaround time, we are looking at the time spent on the entire life cycle of the process, starting from when the process is created to when the process terminates. Okay. Well, the next one closely related to turnaround time is waiting time. Waiting time means the amount of time a process has been waiting on the ready queue. Okay, so it captures only the time the process spends on the ready queue. Okay, so you can imagine that the waiting time is only a portion of the turnaround time. Okay, turnaround time is end-to-end time, starting from the beginning of the process to the end of the process. Well, waiting time is only when the process is waiting on the ready queue. Okay, so during the life cycle of the process may be placed on the ready queue multiple times. Right? It will be placed on the first on the ready queue, and then when it is scheduled, it will be placed on the processor, and then when interrupt happens or when it is waiting for I/O or event, it will be placed back to a waiting state or the ready state. Okay, and when the process is placed back to the ready state, it is back into the ready queue, and it is accumulating waiting time on the ready queue again. Okay, to help you understand this, right? So let's come back to this state diagram. Okay, let's erase all again. So. Okay, so let me use these diagrams to explain the relationship between turnaround time and waiting time. Okay, so first let's simplify it, right? So let's assume there's no waiting. Okay, there's no waiting here. Okay, there's no waiting here. Okay, so this at the beginning I mentioned that, right? So on personal computer, for example, we don't really have long-term scheduler. So a new process is immediately placed into the ready queue, right? So there's no waiting. If we have a long-term scheduler, we have a job queue, right? Then there may be waiting time for a process to stay on the job queue. Okay, but without a long-term scheduler, there's no waiting. Okay, there. Okay, so the process is immediately admitted into the ready queue once it's created. Okay. And then let's also assume that the process does not have any waiting. Okay, let's assume there's no waiting on I/O or event. Okay, and then during the life cycle of this process, the process is either in the ready queue, okay, or on the processor. Okay, so when it is ready state, is in the ready queue. Okay, when it is running state, it is on the processor. Okay, so then the turnaround time would simply, where did I go? Sorry. So would simply equal to, turnaround time would simply equal to the waiting time plus the running time. Okay, so turnaround time, right? Turnaround time is the end-to-end time, right? Starting from the due to the terminate, right? And we assume there's no waiting here, and there's no waiting here. Okay, then the turnaround time equals to exactly the amount of time that the process is waiting on the ready queue plus the amount of time the process spends on the processor. Okay, but again, remember the process may switch between the ready queue and the processor. Okay, when it is ready, we'll go to the processor, and then when it is interrupted, it comes back to ready queue. Okay, so the process may spend time different points of time in the process life cycle. Okay, so it might accumulate waiting time. Okay, and waiting time here is the waiting time on the ready queue only. Okay, and that's what happens. Okay, now if we do not assume this, okay, let me erase it. Okay, right. If the process can also wait on IO event, on IO or on the event, okay, then the process may also spend time on the waiting queue of the IO device or the event. Okay, so now we can see in the waiting state, right? So remember in chapter 3 we also talk about the process, right? The process is not the processor, it's not the processor. The process migrates from queue to queue, right? So we have the ready queue, and then we have a waiting queue for every IO device, and a waiting queue for every event. Okay? Which the event might be for a synchronization event, right? For example, a semaphore. Okay, so if we consider that, right, then turnaround time would equal to, of course, we still have the waiting time. Okay, so this will be the waiting time on the ready queue. Okay, plus the waiting time okay on all the other queues. Okay, and then plus the running time. Okay, then plus running time on the processor. Okay, so only the first waiting time on the ready queue is the waiting time that we're talking about here. All right. So if we consider the whole story, so I don't know why it goes away just by itself, but you got it here, right? Turn time would equal to the amount of time the process spends on the processor and the amount of time the process spends on all the possible queues. Okay, it can be the ready queue, it can be waiting queue on IO devices, or synchronization events. Okay, so no matter what, right, the waiting time is a portion of a turnaround time. Okay, if we do not consider the waiting on IOs or events, right, then turnaround time equals to waiting time plus running time. Okay, I'm explaining this because one of the problems that you need to work on as a part of the homework assignment of this chapter asks you to compute turnaround time and waiting time. Okay, so this is the relation between them. All right. So let me stop here because I want to keep my video short, so it's easier to upload, and we'll continue this night in our next video.